So hello everyone, in this video we'll be talking about permutations and combinations and how they're important for life sciences. So permutations and combinations are a very major part in our entrance exams like JRF, IIT exams and any others or many such courses. Now the thing is that permutations and combinations is actually a topic for mathematics, but now this can, it's such a broad topic that it can be extended to any field you can think about. So for biologists, like we face this problem that we are not from a mathematical background and then we have to start dealing with some problems with permutations and combinations, though these problems can be solved with basic logic also, but things become easier when we have a mathematical model or a mathematical formula to solve them. So let's try to understand this, what permutations and combinations are. But to introduce you with the permutations and combinations, that the permutations and combinations are just like arrangements or just like the choices that you give. It's more like probability. It's more like how you, let's say I give you a situation and then you have to count on. So basically it's about counting. So permutations and combinations are very important for us in the field of biology to work. So I'll be also taking some examples from biological fields so that things become quite easier. To begin with, let's start with the fundamental principle of counting, which is a basic thing which we need to understand before starting with permutations and combinations. So I'll start with the fundamental of principle of counting rather than giving you a theoretical definition or a theoretical explanation. Let's actually try to understand what fundamental principle of counting says. So taking a biological example, suppose that you want to make a tetrapeptide or I want to make a tetrapeptide with the 20 standard amino acids that I have. Now I want to know how many total tetrapeptides can I form with the 20 standard amino acids that I have. So I can consider it as 4 boxes with or 4 spaces that I want to fill basically from 20 choices. Okay. Now I want to know what all tetrapeptides can I make? What is the maximum number of tetrapeptides that I can make? So for the first box, if I consider how many amino acids can I put in the first block? So because I am choosing 20 standard amino acids, in the first block I can only have 20 amino acids. Now if I allow repetition, that there can be same amino acids in the protein, like you can have alanine, 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 alanine. So in that case, for the second block also, again I have another 20 amino acids from which I can choose. So for all these 4 boxes, I have 20 choices. I have 20 amino acids that I can put in these boxes, so that the total number becomes 20 raised to the power 4. Now let's consider another situation that I do not allow repetition. That if I do not allow any repetition, which means that one amino acid, if it has come in one block, it will not be coming in the other blocks. Okay. So again, let's take our box problem. We have these 4 boxes. So suppose I have put 20 amino acids in the first block. Now I'm left with only 19 amino acids that I can put in the second block, because one of those 20 has already been used and cannot be repeated. For the third block, similarly, I will have 18 amino acids to choose from, and for the fourth block, I will have 17 amino acids to choose from, making us to a simple calculation which will be more than 1,15,000 such combinations which are possible. Now let's take it to more mathematical form or more mathematical modeling. We come to a term which is permutation. Now considering the problem which I've discussed so far, that is we have want to make a tetrapeptide. Now what if I select 4 amino acids for you, that these are the 4 amino acids by which you have to make a tetrapeptide. Now still with these 4 amino acids, you still have choice in the arrangement, how you want to arrange the 4 amino acids so that you develop your tetrapeptide. So let's say I give you these 4 amino acids, leucine, arginine, asparagine and lysine. So if I consider lysine at the first position, we can have 6 tetrapeptides which are formed. So now I want to know what all total permutations can I have. So permutation is more like arrangement from a selected or even from the total set of the population that I have. From all the amino acids I have selected these 4 amino acids. And now I want to know, so this is my combination of 4 amino acids. And I want to know what all arrangements or what all tetrapeptides can I form with this particular sequence. So using that box problem again, we have 4 boxes. Now for the first case, I can have 4 amino acids and not 20. Because I have selected 4 amino acids, I have leucine, arginine, asparagine and lysine. I can only select any one of these four in this first block. Now, considering that, in the second block, now I'm left with a fewer choices. I'm left with only 3 amino acids. For the third block, I'm left with 2 amino acids. And for the last, I have no other choice but to push the left, which is left. So in total, I can have 24 tetrapeptides by using these 4 amino acids. So what basically a permutation is, it's an arrangement which is in a definite order of a number of objects which we take some at a time or all at a time. So in this case, we have taken 4 out of 20. Now let's make it more to a mathematical model according to the theorem which is given in NCERT books of mathematics for class 11th. It says that the number of permutations of n different objects when taken r at a time. So for our case, we had 20 different objects, but we are taking only 4 at a time, where 0 is less than r or less than equal to n, and the objects do not repeat. So which means that each of your block is going to have its own identity. They will not be similar. Is given by n into n minus 1 into n minus 2 up to n minus r plus 1. So which can be represented by this formula n factorial upon n minus r factorial. So if I say n factorial, it means n multiplied by n minus 1 multiplied by n minus 2 and so on. So for considering the problem that we have discussed, we try to find out the total number of tetrapeptides we can form. So let's see by using the formula how many tetrapeptides can be formed. So it still gives us the same answer, which is around 1,16,000. Then based on this, now there is another theorem which says if I allow the repetition. So this is the first case that I discussed in the beginning, that I have 4 blocks and I can choose any amino acid that I want to put. So that's how I can have this simple formula n raised to the power r, so that I can have total of 20 raised to the power 4 permutations. Now let's come to what the same example that we had, that I have given you 4 amino acids, but now rather than 4 amino acids, 4 distinct amino acids, the 4th amino acid that I have given is already present in the other 3. So I have 2 leucines this time, 1 arginine and 1 asparagine, and now I want to make a tetrapeptide. Now what is going to happen, because you have 2 similar objects, 2 leucine, before we go into that, let's first ask this question. If I ask you this question, that how many total different permutations can you have for this combination of amino acids? So I'm allowing repetition of one of the amino acids and not others. So let's begin it by considering both the leucine as separate identities. So like we did it earlier, there was a lysine. So let's consider it's L1 and L2. So this one is L1 and this one is L2. So if I consider that, I will have 2 different lysine residues and a total of 24 permutations as we have done it before. Now, but if they are different, they can be arranged as L1 and L2 and L2 and L1, but because these 2 are same, they do not make any difference. L1 and L2 and L2 and L1 are same. So the number of arrangements by which these different similar objects can arrange can be divided by the total number of permutations that are possible to get how many total permutations can now we have when there are 2 same objects. So for this case, it will be 4 factorial divided by 2 factorial, which is 12. Now to move on, the another theorem based on this explanation that I gave you right now, that the number of permutations of n objects, where p objects are of same type and rest all are different, it is given by n factorial divided by p factorial. Now there is an extension of this theorem. Consider we have, let's say, many such amino acids which are existing in multiple copies, multiple similar objects, let's say K, Q, P, N, M, we have multiple. So this theorem can be extended as the 4th theorem, which says that the number of permutations of n objects, where P1 objects are of one kind and P2 are of second kind and so on, we can have this formula where we can divide all these arrangements, all these individual arrangements of the similar kind, which can divide by the total permutations. So we can divide the total number of permutations by the individual combinations or individual arrangements that we can have for those similar objects. Now coming on to combinations. So we have seen that permutations is when you have a definite order. So order is important for permutations. You can have a selected list. You can have just 4 amino acids and still you can create a permutation. But in combination is involved when the order of the, let's say, residues is not important. So it comes with a very classical example that everybody gives. So I will also go ahead and give the same example, that let's say there is a room and there are 12 people inside the room and everybody shakes hand with each other. So how many different hands will be shaken? So this is a very, classical example that everybody gives about combination, because this is a case when order is not important. So how do we solve such a problem? Now, because let's say there is a person Ram, there is a person Sham, and they are shaking hands. So if Ram shakes hand with Sham, or Sham shakes hand with Ram, or if both of them shakes hands two times, that doesn't make any difference. It's just the same. It's just the same hands. Okay. So I can give you a more biological problem similar to that, and by which you can again come to this problem and solve this problem too. So let's consider there is a tetrapeptide. I'm sorry, not a tetrapeptide. Let's say there is a polypeptide and it has four cysteine residues. Okay. And now I want to know how many total possible interactions can exist between two cysteine residues at a time in the protein. So these cysteine residues will be interacting in some or another way. So I know that this cysteine might be interacting with this. Let's say so C1 reacting with C4 is same as C4 interacting with C1. They will not be counted as a separate interaction but the same interaction. Similarly, C2 interacting with C3 or C3 interacting with C2 is a similar kind of interaction. Now I want to find what are the total number of interactions that can exist between the cysteine residues. So I can simply use the formula of combination, which is actually permutations divided by R factorial, where R is your smaller class. So in this case, the total number of cysteine residues is 4. So your N is 4, and because only two cysteines can form interaction at a time, your R will be 2. So using these values of N and R, we get a combinations of around 6, which we can manually also do and see what are all those interactions that can happen between these cysteine residues. Now you can extend this to the 12 handshakes wala question, and you can answer in the comment box. Do like if you like the video, and thank you for watching.